My name is Mike Paday, class of '89. I'm the Associate Vice President for Alumni Relations here at your University of Houston and your mini co-host for today's event. I want to welcome all of you in who have joined us here this evening. I want to remind you a couple simple little housekeeping items before we get started. And I want to get it myself out of the way because we have a great program today. But a few things. One, make sure you're all on mute. We would appreciate that very much. Number two, in the top right corner of your Zoom, you will see you can use what's called speaker view. You'll want to do that as well so that you can see all of our great speakers here this evening when we get started. We will have a Q&A portion this evening after our movie. So you'll want to come back after you watch the movie and join us for the Q&A for that. And of course, we have some upcoming webinars on the UH2U series next week, Thursday, September 24th. We have one on small business with our friends at Bauer College. And we have an interesting one on October 13th about the election. We have some special guests here this evening. I want to introduce the Dean of the College of Natural Science and Mathematics, Dr. Dan Wells is here. Dean Wells, take yourself off mute and say hello so you'll—
Hello, everybody. Welcome to our event. Thank you, Mike.
Thank you so much for being here. We want to thank all of our NSM alums and all of our other alums from around the university who are joining us. Our special guest tonight to get us started, Dr. Julia Wellner is joining us tonight. She's a sedimentologist and a stratigrapher, who works primarily in the Gulf of Mexico and offshore Antarctica on questions related to sediment. And she earned her PhD from Rice University in 2001, where she also completed postdoctoral fellowship. She's been at the University of Houston since 2006, where she teaches stratigraphy, sequence stratigraphy. There's a lot of big words in here. For a hotel restaurant management major, there's a lot of big stratigraphy words in here. Sequence stratigraphy, marine geology, and oceanography. Dr. Wellner also completed over a dozen ocean-going cruises, collecting, that sounds like a lot of fun, collecting seismic data and sediment data, and cores, including 11 in Antarctica. That is quite a resume, Dr. Wellner. And with that, I will turn it over to you, and I will see all of you at the end for our Q&A section. Dr. Wellner, the program is yours.
Thank you very much, Mike and Dan, for welcoming me here. I've never been to an online movie night before, so I don't exactly know what people would expect from this, but I do know it's just a very brief introduction, and that the purpose is to watch a movie and not to hear me give a full-blown science talk. So what I'm going to do now is share my screen, and I have barely any slides, a social amount of slides, not a professional amount of slides. And what I'm going to do is show you a little bit about the work I do and how it connects to this movie. I'm not going to explain most of the movie now. We'll just give a little bit of an introduction. And then afterwards, when we come back for your questions, I can talk about what's true and what's not true for the science in the movie. So the film we're watching tonight is The Day After Tomorrow, and you should now all see my screen with the advertising slide for The Day After Tomorrow. You see that now?
I can see it.
Okay, excellent. So this is a movie night, and we're going to watch the film The Day After Tomorrow, which is now over a decade old, but still seems to be kind of popular, and it does have some very accurate and some very inaccurate science in it. So really quickly, who am I and what do I do? As Mike said, I am a sedimentologist and stratigrapher. I work primarily in Antarctica. I've now spent almost 2 years there cumulatively, and I study the sediments that are deposited on the seafloor. These are a few field photos, and I think some of my students are logging in today, or my alumni, and so if they identify themselves in these photos, please shout out that it's you. But what we do is we work on a ship, and we take samples of the sediment that is deposited on the seafloor. So you can see some mountains covered in snow and ice in the back, and then here's the ocean, and then here's a few people taking a sediment core on a nice sunny day. Here's me taking a sediment core on a really blizzardy, yucky day. And so we work 12 hours on, 12 hours off, 7 days a week for about 2 months at a time to collect these samples. And then we bring them back and study them in our labs. Because the ice sheet is really tied to the ocean, we also study the ocean. And so here you can see a piece of equipment being lowered into the water from the side of the ship. There's some seals out there floating on the sea ice. And here we're lowering this rosette into the water so that we can take water samples and study things like temperature, salinity, dissolved oxygen, nutrients, etc. And then the last picture that I have here is of a couple students. And notice here they're actually on the ice. Because Antarctica is so cold, when we're working on the ship, the ice will freeze around us, and then we can get out and walk around on the ice. It's a little bit disconcerting at first, but you know, these students right here are sitting on maybe about a meter of frozen sea ice, and that sea ice is floating on top of something like a kilometer of water. And I wanted to show you this picture today because that is in the area of the Larsen ice shelf. And you can see these students right here. They've just taken a little hand core, rotating it in and taking a hand-drilled sample of the ice that's floating right there. The reason we do this is so that we can look at the plankton that's at the base of the ice, but other people actually look at the ice itself. I do not. So notice that's at the Larsen ice shelf, and that's what I want to tell you about some more now. So the project that relates to tonight's movie was called Larissa, and Larissa was a project that had geologists, oceanographers, and biologists all working together, and we work as part of the United States Antarctic Program. So my students and I, as well as a group from a wide range of universities, have worked in Antarctica, both ship-based, as shown in the bottom here, and you can see this is an icebreaker. The ship is surrounded by ice. And then we also work via helicopter, at least when we're lucky. We have helicopters that are based on the ship, and then we are able to go onto the ice. And so this is just our project logo. This is the Antarctic Peninsula right here. And this blue is for water, white is for ice. We always use really simple color schemes. And then what you can see here is just this ice sheet breaking up. And that's what I'll show you now. So the Larsen ice shelf was actually very famously broke up in the spring of 2002, the austral fall, so January through March. In the southern hemisphere, that is late summer to early fall. And just like in the northern hemisphere, that's the season that things melt. You know, as we reach peak summer temperatures and then things continue to melt and melt and melt, the early fall is the maximum melt. And in the southern hemisphere, that would be this January to March time. And what these lines show is the extent of the Larsen ice shelf. This land right here, this rough area, is a satellite image showing you where the Antarctic Peninsula is. In this case, because it's a satellite image, black is water, and all of this area is ice. And out here is where the ice was in 95, and then January 02, and then all of a sudden in March 02, it broke all the way back like this. I was actually up here on a ship. We were the closest people on the planet to this breakup. In 02, that is before internet communications at sea. We had no phone. We thought, there's a lot of icebergs, but we didn't really know why. So how did the Larsen ice shelf break up? Here is an image again from January, and all of this area out here is floating ice. This area is called an ice shelf, and that's a very unique type of ice. It really only exists in Antarctica. It's not cold enough in the Northern Hemisphere to have an ice shelf. And so this is a large area of floating ice. And maybe if you look closely at this image, what you can see is that there's some dark strips along it. That dark area is actually a little bit of water, and the satellite image is reflecting that water. Of course, water reflects heat differently than ice does. And so where that water started to pond, it got warmer and warmer over time. That's the albedo changing. And so what happened between January and March is that that water percolated through the ice and broke it out entirely. And so we don't actually have all the satellite images day by day by day. We would now, but there weren't enough satellites at the time to get daily images. So what we see is that if you go from, essentially February 1st to mid-March, that ice shelf shattered into thousands of little icebergs. This was, again, very prominent in the news. This was noted by reporters around the world as a harbinger of global climate change. It was called the canary in the coal mine. It was, well known enough to make a movie. So we're going to start the movie in a minute. And what you'll note is that the movie starts with the movie star taking an ice core right somewhere out here, somewhere on the Larsen ice shelf. He's taking a core to start the film. So we'll go watch that, and then we'll talk more about what's real and what's not at the end. And there's penguins, just to make sure you get a chance to see a penguin in the talk. Thanks. And should I stop sharing?
Yes, so everyone will use the same login to get back in here after the movie. So we will see everyone back here.
So I want to welcome everybody back. I appreciate everybody coming back from watching the movie. This is the first time, we were talking before you all came back, this is the first time we've done something where we said, hey, it's great to see you. Please go away and come back in 2 hours. And we're glad you've come back. We really appreciate that. I want to apologize for something quickly. I learned at the beginning that if you're on Zoom on your phone, you're on video right until you look away to change screens and look at your notes, and then your video goes away. So if you saw me do the introduction a couple hours ago, that's what happened. I didn't know that till it was over, so that's the thing I will learn today, amongst the other things that we learned by watching the movie. So I'm going to punt this back to Dr. Wellner to talk about the movie, and I know she's got some other things that she wants to discuss as well. So Dr. Wellner, I'm going to turn it back over to you.
Thank you, Mike, and hopefully many of you were able to enjoy the film just now. I know some people actually watched it a week ago or a couple weeks ago rather than watching it just now. But I think everybody's probably seen it. And so what I wanted to talk about first is just those 4 minutes at the start of the movie where they're in Antarctica. And I feel very lucky to have been to that part of Antarctica. The Larsen ice shelf where they start the film. It's a isolated, hard to get to part of Antarctica. So there's only a few of us who've been there. But it was so dramatic that it formed the starting point for this movie. But I think this is one of the only times I can name where Hollywood has under-dramatized what happened. So if you think back to the start of the movie, Dennis Quaid, UH alum, is in the shack on the ice, and his 2 assistants are there, and they're taking the little hand core through the ice, just like I showed you my students doing in that location. Except I also showed you the satellite images from when the Larsen ice shelf broke up. And in actuality, it broke into 1,000 pieces. That ice shelf shattered into an infinite number of bergs. So Dennis Quaid jumping across the crack to save his data, and then getting his ice cores and jumping back across the crack. Where did they think they were going? There was no safety place. And, you know, obviously, we just watched an action movie about natural disasters, and any of them are going to over dramatize and make it as dramatic as possible to the point of not being realistic. But this film that we just saw starts with the opposite. It's too overwhelming, I think about the fact that the ice can change so rapidly. There are parts of the ice sheet that change faster than Hollywood even wants to deal with. So that was the start of the film, the breakup of the Larsen. Obviously, that was now several years ago. There was no global climate catastrophe that followed it. In fact, there's not even sea level rise from it. Because that ice is floating, when it melts, when it breaks up, it doesn't contribute to global sea level. You know, that's not one of the issues. But it does drive other more complicated changes. So I did pull up a few different new slides if people have questions, but you know, we can use my slides if no one has any other questions, or if there are questions, we can go that way.
I forgot to make my announcements at the beginning before I kicked it back to you to remind folks, if you have a question, please go ahead and put it in the chat, and I will see those and call on those and call them out as we go. And we might even be able to unmute some folks if we get a great conversation going on. So we do have a question from Sarah. Is it even possible that temperatures could drop 10 degrees a second? Dr. Wellner.
I don't know, maybe, yes. They wouldn't drop by cooling the same air mass, though. So I think it would be really difficult to, in the air or the ocean, drive that much change by cooling. On the other hand, you can have winds that drive really rapid changes. And so that can blow hot air away from a location, blow cool air in. And we could certainly get, I don't know if 10 degrees in a second, but we could certainly shift the location of air masses and get very rapid cooling.
So excellent question and excellent answer. Nancy has a question that says, what were the realistic consequences? Supercooling almost as fast as people can run, etc.
No, not supercooling as fast as people can run. But, you know, so sort of the beginning of the movie when they go to India and they have the IPCC, the Intergovernmental Panel on Climate Change conference in India, and they're talking about global ocean circulation. And then when they show the buoys around the North Atlantic and how those buoys are recording change, that part's relatively realistic. And then as we go farther and farther through the film, it gets less and less plausible. So, you know, the basic premise there was that the circulation in the Atlantic would shut down. And if you've never thought about ocean circulation before, I think you can still pretty easily understand what happens in the Atlantic because it's sort of a simple system. In the Atlantic, heat moves northward. And that is why the same latitude in the Carolinas is warmer than that latitude in California, for example, is we're transporting heat northward. That's driven by this ocean circulation, the thermohaline circulation, where sort of ice formation and ice melt off Greenland. Remember, Greenland's in the North Atlantic. And as the ice in Greenland grows or retreats, waxes and wanes, that drives the ocean to change. And again, that's really good that we asked, you know, we got these two questions in this order because what the premise is of this really dramatic potential cooling in the Atlantic, it's not about cooling the same water mass all of a sudden, but rather changing the way the circulation happens, and therefore not bringing the heat northward. So would you have to run from supercooling? No. But could we stop bringing this warm water up the coast of the Atlantic and over to England? Absolutely. That could change.
All right.
Okay.
Jasmine asked how much of the depiction of the North Atlantic, circulation is real and how much isn't?
It was pretty accurate. You know, I have, if we pull up my screen, I can show you a slide, but, you know, it looks just like the figures they showed in the pictures in the movie. You know, when they're at the NOAA office, the National Oceanic Atmospheric Administration in DC, and they show on the computer screens the ocean circulations, those are the same figures I use in freshman oceanography at UH. I mean, those are real basics of ocean circulation. That part is very much real. And the idea that it could shift does come from the record of geologists. You know, and this is where we get into a situation where I think the outside view of geology is, you know, somebody hiking in the mountains with a backpack, or you know, making a map, maybe looking for oil. The type of geology I do is connected to the ocean, right? I don't study mountain building. I study ocean circulation and how the ocean and ice moves and changes where different parts of the ocean are, you know, a certain way. And so, and, you know, on a very modern way. So that part's all very accurate and something we teach our students.
Great. So the next question is kind of a long one. And while I ask it, I believe if you wanted to share your screen, you could do that. If you had something you want to show, I think you have the access.
Okay.
While
Yeah,
I read this question. So Brian says, it seems like everything is being blamed on climate change, stormier seasons, wildfires, etc. But yet one summer a trend does not make. How many times in a row does it take to officially make a trend that points to real climate change?
So that's a great question. And you're absolutely right that we need to think about the difference between climate and weather. And weather is that daily or weekly or monthly condition that we experience, you know, in real life. And maybe we could have a hot summer or a cold summer. And in the movie, we certainly get to looking a lot about storminess. And again, it's all made up, so it's hard to say when they cross from being climate to weather because it's, you know, not plausible anyway. But if you're thinking, if your question is about reality and not about the movie, one hot summer is just a hot summer. One hurricane is just a hurricane. One extra large hurricane is just one storm. A season or two of lots and lots of hurricanes is just a season of lots of hurricanes. However, if we look at, and I didn't pull up slides to look at, you know, actual temperature change or trends in climate change. But if we look at, for example, average temperature for the last 150 years, year after year after year now, we are over average. And then the same goes for, you know, a variety of other measures. Ocean temperature is the major changing change that we're observing. It's not just air temperature, but ocean temperature. So one season, you're totally right. It's just weather. But what we have observed now is year after year after year after year. The other thing that I can add to that is my personal thing that I study is sea level rise. I don't study storminess or, air temperature, because there is so much fluctuation in that. There is a lot of, well, is that a trend or is that just an anomaly of 1 year? Looking at sea level, though, it's a pretty simple system. It's just going up and up and up and up. And so what we reconstruct is a very clear signal, and that's why I like to focus on that.
Excellent. I had a quick question on my own. When you, or maybe not just you, but other people in your department see the map that you saw last week where there were, or maybe it's even today, where there are like 7 storms at one time going on in the Atlantic or the Caribbean. Where does your brain go, or what is the hallway like in the building, or maybe not in the building now because we're not in the
I don't know. I don't go to work. So
but, okay, in the old days, pretend we were at work. What would the building be like when you saw a map that had, let me just say, letters S through W, and we're about to go to alpha, right? What is
we're
that?
going to the Greek alphabet, and this is only the second time. The other time we went to the Greek alphabet was in 2005. Right. And of course, that was the year of Katrina and Rita. Right. So it wasn't random that I used that as an example just now. That we are in a very active hurricane season. Climate scientists and atmospheric scientists have known for decades that what controls hurricane formation is ocean temperature. And just like I said a minute ago, air temperature is on average rising. So is ocean temperature. And the warmer the water out there in the Atlantic, and particularly in the Caribbean and the Gulf of Mexico, which are these enclosed seaways right here, and therefore are able to warm up even faster, like a bathtub compared to an ocean. That warm water feeds more and more hurricanes, and they can grow more rapidly, as we observed with Laura. So yes, no one hurricane can be contributed or attributed to climate change, but ongoing increases of more, faster, stronger, bigger, longer certainly can.
Wow, great. Because I know my eyes light up when I look out there seeing I'm running out of alphabet, what's next? And then, I get tested, now what is the Greek alphabet? Okay, so that's a story for another day. Okay, so Mike has a question. Is light reflecting off ice or snow cumbersome in Antarctica? And 2, could satellites, MIROS, reflecting sunlight cause and affect change?
Okay, I'm going to answer the first question, then ask you to repeat the second one.
Okay.
Because I didn't get it. So is light reflecting off snow and ice in Antarctica cumbersome? It can be, yes. And so, if your question is about people, here's an example of scientists observing penguins, and you can see it's a little bit cloudy that day. But most of the time it's very, very bright and everything's very, very white. And so we certainly do have to spend most of our time in sunglasses or goggles or other material like that. And you can go back and see that here. You can see us, in this bright sun, and the ice is reflecting it. It has that high albedo that's reflecting light, and it certainly leads to sunburn and stuff. When I first started working there was still a pretty big, large hole in the ozone layer. And as you may know, ozone in the upper atmosphere is what protects us from UV rays. And so if you were working in Antarctica when there was still a ozone hole, we actually had to be extremely careful of sunlight because that shield was not there in the atmosphere. That has largely healed, and that problem has gone away. And then the other aspect I wanted to mention about that question, again, you can see everything's icy, so yes, it's bright. Remember I mentioned these dark areas when we were talking about the Larsen breaking up. So the Larsen ice shelf, remember, was this floating ice that got just a little bit of water on the top, just a few small areas, but then that dark area of the water absorbs heat more rather than reflecting it like snow and ice. And then the water area grows, so it absorbs more heat. This is a positive feedback loop. And so the reflectivity of ice versus water is a fundamentally important question in everything. And
Awesome.
then what was the second question?
So Mike looks like a very friendly person, and I like his background. So if he wants to unmute himself, Mike, if you can unmute yourself, you can go ahead and ask your question. Kendra, can he unmute himself? Yes. Go ahead, Mike, because I don't want to mess up your question. It's so intelligent, and I'll read it wrong. You go ahead.
I think my microphone might be a little...
No, you're good. We can hear you clear. We can hear you
webcam.
clear. Yep. Go ahead.
I think I'll just say the same question, but let me know if this helps a little different. Could satellites reflecting sunlight cause or influence a change in Larissa or in some system?
The satellite itself.
Yeah, like maybe by accident or maybe a specific instrument to focus
probably
light.
not, but I'll give you the same answer I try to give students. Like, maybe, theoretically, you've just brought up an interesting idea that if we're putting satellites up there with a bunch of solar panels, and those solar panels, because that's how a lot of satellites keep going, is they have solar panels to recharge their batteries. And so theoretically, they are reflecting light away from Earth and absorbing it up there, in orbit, not letting that light come down and reach the Earth. So yes, you're right. You've just thought of a new way that we are limiting the amount of the sun's energy that's reaching Earth's surface. On the other hand, I think it is so small, it is so minuscule that we would need to put up countless more satellites for it to make a measurable impact.
Thanks, Mike. And don't tell Elon Musk that, because he might try it. So we might put up 5,000 more satellites. Okay, so we are planning to go about 10 more minutes, and we do have 2 questions in our till, and they look like they're very in-depth. So I'll give you Sarah's first question. At the end of the movie, the astronauts were saying the air was so clear after the storm passed. She didn't really understand that. Do storms affect air quality?
Totally. I mean, in Houston, if it's a really bad pollen day and it rains, the pollen's cleared out. In California right now, which is where I'm from, the area is absolutely totally covered and suffering from wildfire smoke. And yes, that's reaching across the US now, but that's because there's there's winds coming to California and blowing it away. So rain clears the air, wind clears the air. We talked about pollen and smoke. The same thing goes for pollution. Anything in the air can be blown away or washed away.
Now, I do find it amazing. We had that Saharan dust situation back in June, how far Saharan dust traveled across the globe, all the way to Houston for what, 5 or 6 days of bad air quality.
You're absolutely right, and that is remarkable that we can track it with satellites now, and that we can see the plume coming across to the Gulf Coast. But don't forget that Saharan dust is also what triggers hurricane formation. So the circulation pattern of hurricanes doesn't just start at random. It usually starts with an area of a lot of particulate matter in the atmosphere.
Wow, that's fantastically informative for me, I can tell you. Okay, so we have a couple more minutes, one more question in the queue. You just mentioned the ozone layer being largely healed. That took tremendous commitment from around the world. Do you think we could do that for or with climate change and help heal that? Is that possible?
Okay. So, of course, I am a scientist and not a politician or a policymaker. And so this question, even more than the others, is asking about people and policy. So I'll give a short answer. A lot of what I study, again, is the Antarctic ice sheet. That is what I know the most about. And where we are studying it, in particular, I study the area that has been called the weak underbelly of the ice sheet, or the keystone, the piece that's holding up the rest and is thought to be susceptible to change. I will show you, just one more figure here. That was just if I talked about climate tipping points. This is our cruise this year. This is in front of the Thwaites Glacier. We didn't have helicopters this year. This is just a drone picture we took during the lifeboat drills. So this is the icebreaker I work on. And then this is the quarterly test of the lifeboat going around us. And this is the Thwaites Glacier system behind us. And this is just a cartoon to explain how glaciers behave and why I'm going to say, no, we can't solve it. As hopefully everybody understands, the planet is warming, air warms, and the ocean warms as well. And water has a very high heat capacity, and that means it's taken up a lot of the warming so far in the planet. It's not as obvious to most people, but the ocean has absorbed much of the heat as the planet has changed. And that drives ocean warming, and that takes a bit longer to happen. But now we've warmed it. Let's say we've warmed the ocean in some places. So I study Thwaites Glacier in West Antarctica, which is a glacier like this one in this cartoon, where the ice, shown in white here, is sitting in contact with the ocean. And of course, you know that ice is frozen and water is not. And that means the water is warmer than the ice. But we have just warmed the world's ocean a little bit. And that water is just now percolating up to the Antarctic ice sheet. So what most of us that work there believe is that this retreat has already started. And that's why year by year right now, you see more and more retreat of the Antarctic ice sheet. And we can't stop this warming. The commitment has been made. And even let's say we stop every bit of CO2 burning tomorrow, which of course we can't. If we stopped at 100%, that warm ocean is still flowing towards the base of the ice. So the ice will still retreat farther, and then farther and farther, and raise global sea level a great deal. And then this is the last diagram that I would end on to predict how much would global sea level rise. And this is a diagram just of, it's really the building block of the entire group I work in, to think about how much can Antarctica contribute to global mean sea level. And you see there's a range of projections over the next 100 years. Some of them are very low, but some of them are very high. This prediction is from 2016. And in the 4 years since, we have been starting to follow the upper curve. And that's pretty true of all the predictions. That year after year, scientists say, oh, we don't know if it's going to be 1 meter or 10 or 1 degree or 2, whatever it is. And it keeps coming out on the upper end of those estimates. And of course, that doesn't mean scientists were wrong. It means that we learn as we get more data and refine models and step forward, and that, sea level is going up.
Got it. All right, we have one more question from Kathy. At the beginning of the movie, scientists said that the melting of the ice shelves was lessening the saline content of the water.
Yeah.
which caused the huge storms to form. Is that really plausible?
Sort of. So yes, so in both the southern and northern hemisphere, ice is melting, we know that. And as the ice melts, it adds fresh water. You know, there's no salt in the ice. So that fresh water is added to the ocean. And then that sort of interrupts the way the ocean circulates. So that part is 100% clear and accurate. True in the movie. How does it lead to storminess is a little bit more complicated. It certainly changes things, and I think we can leave it at that.
All right, so the last question I have is just for you, for me, for fun.
Okay.
What excites you the most about what you do? Like when you wake up, like what's the next thing that's super exciting that you want to get your hands on, and as a faculty at the University of Houston, and you know, you have to do these things, but if given one chance to do something, what would it be? What do you want to really jump into?
I mean, to tell the truth, I think I have a pretty extraordinary set of opportunities already. You know, I'm not pining to try something new, because I think that getting to work in Antarctica and take a ship to a place where no one else has ever been. This is my cruise this year. This photo was taken in March. There's 2 UH students out there. Being able to be the first person ever to see a part of the world is, I think, as lucky as I could be. And being able to teach new people and bring students there and show them and teach them why it matters is pretty lucky.
That is pretty awesome. And ironically, these may be the only cruises that are still on the oceans. So
they may not be next year, actually.
Oh no, I'm sorry to hear that. Well, thank you all for joining us. Dr. Wellner, thank you so much for your amazing talent and your insight. Thank you all for joining us and watching the movie today. I mean, we're going to do this again. We'll do another opportunity. We have some links in the chat for you if you'd like to follow Dr. Wellner's research. I'm sure the College of Natural Science and Mathematics would love to have your continued support as a group. I know Dean Wells is here, and Janice Parsley and Stacy and everybody who has anything to do with that particular college, which is just an absolute rock star college at the University of Houston. We so appreciate everybody's time today on a Friday. I will tell you a little side note. I did ask Mr. Quaid to attend today, and he could not attend, but he wanted me to send along his best wishes to everybody. And he said that was one of the most fun gigs he ever had. So
you should tell him that he could talk to someone who's actually been there.
I was trying to get him to sneak in and say hello today, but his calendar would not allow it. But I wanted you all to know that he was honored that we had selected something that another alumnus was in. And he said, what's the name of the movie with the dog that he just put out? What Kendra will tell me. He just did that Best Friends dog movie. Anyway, his text was, besides the movie with the dog that made everybody cry, that was one of my favorite movies I've ever done. So anyway, you'll have to Google that, but it was one of those, friendship dog movies that was out a couple years ago. And
Dog's Purpose?
What was that?
The Dog's Purpose?
That sounds correct. That sounds it. Thank you, Alyssa. I appreciate that. Let's not watch that because no one will be able to come back because there's not enough Kleenex in the room if you have watched that movie. So thank you all for joining us. Again, we have a webinar next week on small business. We have one coming up on elections in a few weeks. We encourage you to go to houstonalumni.com and click on the webinar. We will be recording this. Well, it is recording. We will be posting it with all of the information. We'll put a space in there that this is where you should watch movie, and then come back for the chat. And we thank all of you for participating. Dean Wells, thank you so much for joining us today. Thank you all so much. Kendra, thank you for running this with us. Thanks for everybody for all their hard work in putting this on and the collaboration. On behalf of everybody, like I always say at the end of these, good night and go Cougs. Thank you all very much.
Go Cougs.
Bye-bye.
Thank you.